Hello, my name is Vadim Grinberg, and today I'm going to present you our joint work with Uriel Feige, How to Hide a Clique. We start our discussion with maximum clique problem in a random GNP graph for p equals 1/2. It is well known that the size of the maximum clique in such graphs is approximately 2 log n with high probability. However, we don't know any polynomial time algorithms that find such cliques. There is a polynomial time greedy algorithm that finds a clique of size close to log n, but the existence of constant rho greater than 1, such that we can find a clique of size rho log n in Gn1/2 in polynomial time, is a major open problem. Same applies to the maximum Adversary problem. In classical planted clique problem, we take a random Gn1/2 graph G prime and make a random subset Ck of k vertices into a clique by adding all missing edges within Ck, obtaining graph G. We say that G has a planted clique of size k and denote this model by Gn1/2k. One can think of three possible algorithmic goals in this model: find the set Ck itself in G, find the maximum clique in G, or find any k clique in G. It is not hard to show that for k large enough, say at least 3 log n, with high probability chosen vertices Ck form the unique maximum clique in G. So all three goals coincide and we can focus on just finding Ck. How large should k be to be able to find Ck in polynomial time? In 1995, Kuchera showed that when k is greater than the square root of n log n, with high probability, Ck is simply the set of k vertices of highest degrees in G. Later, new polynomial time algorithms for smaller values of k were discovered. Plenty of different approaches have been developed for k being some constant times square root of n. The first algorithm, by Alon, Krivilevich, and Sudakov, was based on special techniques and also allowed to make the constant in front of square root of n to be arbitrarily small, sacrificing polynomial factors in the random time. Some other notable algorithms include lowest theta function-based algorithm by Feige and Kraus-Gamer, the reverse greedy principal approach by Feige and Ron, and message passing algorithm by Deshpande and Montanari. For values of k much smaller than square root of n, there have been many attempts to find polytime algorithms, but so far all of them failed. The existence of any polynomial time algorithm for such k is a major open problem. The planted clique problem for smaller values of p has not been studied as thoroughly, but still is quite well understood. When p is n to delta minus 1 for some delta between 0 and 1, with high probability the size of the maximum clique in GNP is bounded by a constant. This extends to the planted clique model GNPK, regardless of values of k. We are not aware of such results being previously published, but they are also not difficult, and we will return to this later in the talk. For maximum independent set in GNP with this p, it is well known that the size of the maximum set is approximately n to 1 minus delta log n. And known algorithms extend to finding planted in sets of size n to 1 minus delta over 2 for planted independent set model, which we denote by overlying GNPK. In this talk, we introduce a variation of the planted clique in set model that we refer to as adversarial planted clique model. Similar to random planted clique, we start with random GNP graph G prime and parameter k. Then, computationally unbounded adversary inspects G prime and selects k vertex set Ck of its choice, and makes it into a clique obtaining graph G. We refer to this model as A GNPK, and the corresponding model for planted independent set as A overlying GNPK. In the adversarial model, it is no longer true that planted clique is clique of maximum size in G. Moreover, the k clique Ck may be indistinguishable from some other cliques of size k. So, the three goals of finding Ck, finding max clique in G and finding any k clique in G are no longer equivalent in the adversarial planted setting. Our results for adversarial planted clique and planted independent set model cover a wide range of values of probability P. But for simplicity of presentation, we will focus on 3 representative regimes, each corresponding to particular values of P. The first regime is P equals 1/2. Here, for adversarial planted clique model with k equals epsilon times square root of n for arbitrary positive constant epsilon, we claim that there exists a polynomial time algorithm that with high probability finds maximum clique for every adversarial strategy. The second regime is P equals n to delta minus 1 for delta between 0 and 1. Here, for adversarial planted clique model with arbitrary clique size k, there also exists a polynomial time algorithm that with high probability finds maximum clique for every adversarial strategy. The key point is that with this P, we have no lower nor upper bound on the value of k to be able to find the maximum clique in polynomial time. The third regime is P equals n to delta minus 1 for delta between 0 and 1, but now we consider adversarial planted independent set model. We claim that for planted int sets of size k, where k is much larger than n to 1 minus delta and at most 2/3 n, here constant 2/3 was chosen arbitrary and can be replaced with any constant less than 0. For these values of k and p, there exists no polynomial time algorithm that finds any independent set of size k with constant probability unless np equals rp. We are going to present a brief overview of the proofs for each of the 3 regimes. First, we discuss the algorithm for adversarial planted clique problem with p equals 1/2 and k being constant times square root of n. Our algorithm is based on theta function of lowest. It is important that we can compute lowest theta function in polynomial time using semi-definite programming, and also the clique number of a graph is upper bounded by the lowest theta function of its complement. In the work on polynomial time algorithm for randomized planted clique problem, Feige and Kraus-Gamer showed that for graphs in Gn1/2 k model with k at least square root of n, with extremely high probability, the clique number of the graph is equal to the lowest theta function of its complement, and both are equal to k. Unfortunately, in adversarial planted clique model, clique number and value of lowest theta function are no longer equal and can be different from k significantly. This is because, unlike in randomized model, planted clique may not be the maximum one, and also adversary can plant the clique so that lowest theta function is much larger than the clique number. Moving to our algorithm, let Ck denote the planted clique in Agn1/2 k and C* denote the maximum clique. One can observe that with extremely high probability, for every adversarial strategy, C* and Ck differ in at most log n vertices. So we can expect that since the maximum clique is not very different from the planted k clique, the value of theta function may also be not too far from k. This is exactly the case, and in our work we show that for adversarial planted clique model with k, at least some large constant times square root of n, with extremely high probability, theta function of complement graph is at least k, and at most k plus big O of log n, for every possible adversarial strategy. To prove the theorem, we consider an equivalent formulation of lowest theta function as an eigenvalue minimization problem, where we minimize the maximum eigenvalue of matrix M such that it has entries 1 for every h present in graph G and arbitrary values in the other entries. We introduce matrix M with these properties such that its maximum eigenvalue is at most k plus log n, which gives the desired theta function upper bound. As for the algorithm itself, The first thing we do is compute the theta function of the complement graph, using semi-definite programming formulation of it, where we maximize over all orthonormal representation Si of complement graph and unit vectors H. Having obtained the optimum Si and H with extremely high probability, the optimal sum value will be at least k, and at most k plus b co of log n. Let H be the set of all vertices I such that their contribution to the optimal sum is at least 3/4. One can show that with extremely high probability, set H and magnetic clique Ck differ in at most big O of log n vertices. Recall that maximum clique C star also differs from Ck in at most log n vertices. Using these facts, we can consider set F of all vertices I that have at least 3k/4 neighbors in the set H. We prove that with extremely high probability, this set F contains all vertices of maximum clique C star and at most big O of log n additional vertices. So we have set F that contains max clique of graph G and at most big O of log n additional vertices. The latter implies that the subgraph of the complement of G induced on F has minimum vertex cover size at most big O of log n. Therefore, we can find the minimum vertex cover in this graph in polynomial time, for example, via the algorithm used to show that vertex cover is fixed parameter tractable. The algorithm goes over every edge and tries including each of the endpoints into the cover, deleting the other endpoint, and continuing recursively on the resultant subgraph. Since the size of the minimum vertex cover is bounded by big O of log n, we have the depth of recursion at most big O of log n. So the random time, which is exponential depth, is polynomial in n. Having found the minimum vertex cover in the subgraph of the complement, we immediately get the maximum clique in the original graph. To reduce the constant in front of square root of n in the k value, we use essentially the approach of along Krivulevich and Sudakov. We guess constant number of vertices from planted clique Ck, trying all possible subsets, and consider the subgraph of G induced on their common neighborhood. This subgraph Gt corresponds to the subgraph of Gn1/2 with planted clique of size k, t, and size nt of Jt and the value of kt allow us to apply the earlier algorithm to this subgraph Gt, finding maximum clique in it. After that, we combine the found maximum clique in Gt with t guessed vertices to obtain the max clique in the original graph G. This finishes the algorithm. Now we move to the second regime, the adversarial augmented clique model with p equals n to delta minus 1 and arbitrary size k of the planted clique. Our approach for this case is rather simple. First, one can observe that the expected total number of cliques in the random GNP graph with such p is at most polynomial in n. Of course, in the planted setting, the number of cliques may be large, as we can take subgraphs of the planted k clique. However, the number of maximal cliques in G taken from A, G, and K must be small. One can observe that every maximum clique in G is uniquely determined by its subgraph that does not contain any vertices of the planted clique, while being the clique itself in the original GNP graph. This is because to get a maximal clique in G, we can take some clique in original GNP and add its common neighborhood in the planted clique. As a result, the number of maximal cliques in G is at most the total number of cliques in the original random graph, which, as mentioned earlier, is bounded by polynomial in n. Using these observations, we do the following algorithm. Just list all maximal cliques in G and output the largest one. It was shown by Makina and Uno that we can list all maximal cliques in time linear in their number times some polynomial in n. As we can see, the algorithm works regardless of what the size of k of the planted clique is for every possible planting. Now we move to our third regime, the adversarial planted independent set model with p equals n to delta minus 1 and k between n to 1 minus delta and 2n over 3. We need to mention that our algorithm for e equals 1/2 fails here, since our proofs can guarantee upper bound on theta function only k plus a big O of n to 1 minus delta log n. So we can't guarantee that we will find the vertex cover in polynomial time in our final step of the algorithm. We actually are going to show that there is no polytime algorithm that can find any k in set in adversarial planted independent set for these parameters with constant probability unless np equals per p. Assume for contradiction that we have algorithm alg that finds k in set in G with constant probability for every adversarial strategy. We'll use alg to solve hard instances of max in set problem. We now introduce a class capital H of graphs that we will use in our hardness proofs. Graphs from this class shall have three following properties. Solving max in set on graphs from H is NP hard. These graphs are very sparse, and the number of vertices in each graph is small. To be more precise, we take calligraphic H as a class of balanced graphs on n to epsilon vertices for some small constant epsilon, and to average degree 2 plus delta. The graph is called balanced if no subgraph of it has average degree larger than the average degree of the original graph itself. In our work, we show that solving max in set problem on such graphs is NP hard. Let K prime and H from class calligraphic H be a graph such that determining whether H has an int set of size K prime or not is NP hard. We use alg to find K prime inset in H if there is one. To do so, we apply the following algorithm algorand. First, generate a random GNP graph G prime. Then, plant a random copy of H in G prime. By planting, we mean choosing a random set of vertices and turning the subgraph induced on them into H. Next, we plant a random int set of size K minus K prime within the non-neighborhood of H in G prime, obtaining graph G. It is important to note that the planted independent set of size K minus K prime with high probability will be the maximum in set in the non-neighborhood. Finally, we run alg on the obtained graph G. If alg outputs some K in set I, then with high probability I contains at least K prime vertices from H, which form an independent set in H. Since we know which of the vertices of I are from H, we thus find a K prime in set in H. If H has no independent set of size K prime, algorand clearly fails to output K in set. The question is, why shall it succeed if H actually has K prime in set? The reason is that algorithm alg used by algorand is fooled that the graph G is run on the graph generated from A overlying GNP-K model. And on such graphs, alg finds independent set of size K with constant probability. Why is alg fooled? This is because distribution of graphs generated by algorithm algorand is statistically close to the distribution created by adversary in adversarial planted clique independent set model. Consider the following adversarial generation process to better understand the reason why distributions are close. First, we generate random GNP graph G prime. And then adversary finds all copies of H in G' and selects one of them randomly. Next, adversary plans K in set as follows. K' vertices are chosen from the independent set of H, and the rest K minus K' vertices are selected randomly among the non-neighbors of this copy of H. We claim that the resulting distribution and distribution generated by L-Grant are statistically similar. Why are two distributions statistically similar? Let's compare the two graph generation processes of L-Grant and of adversary respectively. The key difference here is that L-Grant plans H randomly in GNP, while the adversary chooses a random copy of H that is already in GNP. It turns out that planting H into GNP, L-Grant does not change the random graph too much because it already had plenty of copies of H in it. More specifically, we show that for class calligraphic H of balanced graphs on n epsilon vertices with average degree 2 plus delta, the expected number of copies of H from this class that occur in GNP is high, and with high probability, the number of these copies itself is close to expectation. This means that adding another copy of H into GNP, which is done with L-Grant, will leave the graph GNP roughly the same, and algorithm ELG is fooled that this planted copy of H is actually a copy of H that initially was in the graph, but got selected by an adversary. As a result, we would be able to find an independent set of size K' in H with constant probability in polynomial time, because ELG works with constant probability in polynomial time, which would imply that NP is equal to RP as desired. Concluding the talk, we would like to mention a couple of interesting open questions related to the topic. First, what happens if we choose parameters P being some large constant over n and K being some small constant times n? Our results do not cover such low values of P, and no algorithms for randomized blended clique model, for example, the one by Feige and Ofek, seem not to extend to adversarial setting. Another interesting question is considering the so-called mirror model, where the original graph G' is chosen by the adversary, and then a random K clique is planted in it. For most values of P and K, we don't know neither if we can find any K clique in polynomial time, nor if the problem is NP hard for certain values of parameters. Thank you for your attention.